Okay, so today we're going to talk about heating and cooling curves, which is just an extension of how we discuss our states of matter. But before we do that, I wanted to do a quick review as far as from yesterday. I looked over some of your particle diagrams, and remember, the particle diagrams are very important. You saw them on the exam, and you will continue to see them, especially with this unit as well. And I saw that together, the example we did together, remember when water is a solid, it doesn't look like most solids. There's actually space in between the particles, which is why we did our solid like this for our example. But remember in your particle diagram, not every example that included a solid was water. So when you do your other samples that aren't water, make sure they're similar to this one. Okay, most solids, all the particles are literally stacked on top of each other, and then they can only vibrate. So we just do the vibrate symbol on the outside, but make sure they're stacked on top of each other. Remember, water is an exception. It's special. It's the only one that has space. So if you have a solid in your particle diagrams, okay, and we see that up here too, just make sure all your particles are stacked on top of each other and just put the vibrations on the outside. Okay, just clearing that up. But anyway, let's get back to what we got to do today, and that is heating curves. So what you have in your digital notebook is a heating curve, and it's blank, so we're going to label it together. A heating curve is pretty much a graph. So when we read graphs, we have to make sure we pay attention to our axes so we read them correctly. So at the bottom here, it says heat added. So it's going to show how a substance, in this case, our substance is water. It's going to show how the phases of water change as you add heat to it. Because like we saw yesterday, the phase of matter is directly dependent on the temperature, right? So the water that we experience is liquid. That's because we normally experience at a certain temperature. But remember, when it's super cold, it's ice or solid. And then if it's super hot, at that point, we can't see it anymore, or it's a gas. And that's what this graph is going to show us. So the first thing we'll see is the first line. So the first line represents water in the solid state. And if you pay attention, like I said, to our axes, they're giving us our temperatures. So pretty much any temperature below 0 degrees Celsius, you're going to find water in the solid phase. And make sure you write solid only. That means from this entire time, so from 0 and down, that goes down to -40. But clearly, if you go under -40, okay, no changes. It's still going to be super cold. It's going to be solid. Then at this point, does anybody know what's special about 0 degrees Celsius with water?
Freezes.
What?
It freezes, right?
Right. That's the freezing point, right? But in this case, we're adding heat. So what's going to happen at 0 degrees Celsius?
It's also going to change into like a liquid, maybe.
Right, and that means it's going to melt. Exactly. Thank you, Sam. It's going to melt. So in this case, now we're going to end up getting liquid and solid because now our melting process starts. So this is where you have liquid and solid. So at this point, this special point, this is where the liquid appears. So if you want to add that to your notes, I would. Okay, I know I didn't leave a text box, but you can always create your own text box as a reminder for yourself. This is where the liquid appears. And we've seen this, right? When you get a ice cold beverage, you usually have the liquid and you see the ice cube floating around. And eventually, if you leave it out enough, right, it's going to end up adding enough heat just from the surroundings. And then that entire ice cube goes ahead and melts until you're left with all liquid. And then here is when we have liquid only. And we have liquid only for water for a long stretch between 0 degrees Celsius all the way up until, and I can trace this over, 100 degrees Celsius. Because remember, 100 degrees Celsius is another important temperature for water that we'll discuss in a few. But room temperature is around 20 degrees Celsius. And if you think about it, I know we don't measure temperature in Celsius, we measure it in Fahrenheit, but for the most part, as far as the atmosphere and how our planet works, normally we're somewhere between 0 and 100 degrees Celsius, definitely nowhere close to 100 actually. So that's why the water we see for the most part is always in the liquid phase, right? That explains why water is so great for our planet, because it has a very long time that it stays liquid, which is what's necessary for us. Remember, our bodies are mostly liquid too. However, what's special about 100 degrees Celsius with water?
Water starts to turn into a gas.
Right, it's about to turn to a gas because that's the boiling point, right? So at this point, as soon as you hit 100 degrees Celsius, it's like, uh-oh, now we have gas and liquid forming. So in this point, this is where your gas appears. Luckily for us, it doesn't just vanish and becomes gas, because that would make things super unstable. Also, when you're cooking, right? I do it all the time, especially when I cook pasta. I'll turn the heat on high and then I'll walk away and just wait for the water to boil. If every water molecule immediately became a gas, I'd burn the house down, because then I'd just be burning the pot. There'd be nothing left to boil. So in this case, you have all those liquid particles. Eventually, they all end up having enough energy, or you add enough heat, get the temperature high enough, so now all of a sudden you have no liquid, and then you'll end up having only gas. So that's the situation we definitely don't want in the kitchen, right? Don't walk away too long, because once all of that liquid disappears and you have only gas, that's where you get in trouble. And like I said, you can accidentally burn the house down. So this is the heating curve for water, but pretty much all heating curves have the same shape for most substances. Most substances at different temperature exist as a solid, or as a liquid, or as a gas. The only thing that's going to be different for other substances is the temperatures at which they change. So that's why it's important to use water, since that's the one thing we've all experienced in every state, but just understand the shape, more importantly, of how this heating curve works. And it's called a heating curve because I'm adding heat. So I'm increasing the heat as I'm going up. So if you think about it, like I said, I don't know why anyone would do this, but if you had a pot with an ice cube in it, you would literally watch it go through all these phases. Starts off as an ice cube. As you add heat, you see water forming, and then eventually it's all water for a very long time, or a longer time at least. And then you start getting those bubbles and creating your water vapor as it escapes into the gas phase. Right. And that's what we're going to talk about now, how this actually shows us the processes too, or the phase changes we talked about yesterday. So here, and you have this in your digital notebook, now we have processes. So notice your processes, I'll put it here, processes, AKA your phase changes. They happen at the flat lines. Or if you want a nice fancy word, they happen at the plateaus. So here, okay, is where we have melting and freezing, and here is where we have condensation and evaporation. Now, remember yesterday we saw this. Somebody remind me, why am I using red and blue? What does the red indicate?
Heat and hot temperature.
Right, I heard a lot. Can I get one? Sorry. As far as red, are we adding heat or taking away heat for the red stuff?
Adding heat.
Right. For the red, we're adding heat, and then for the blue, we're doing what?
We're taking away heat.
Right. Take away. Take away, remove, or in other words, we're cooling it off. And I have that here so we can read the graph, and also understand that we normally read as people, right? English language, left to right, but we can also read right to left with these. It just depends on if I'm adding heat. So at this point, let's go. So here, 0 degrees Celsius, if this is water, right? As I'm going from solid to liquid, melting is happening because I'm adding heat. However, if I'm at this temperature, the melting point, and I'm deciding to take away heat, freezing is going to occur. So in that other box you have, this is actually the melting point and the freezing point. So if you want to relate this to water at 0 degrees Celsius, okay, if I'm adding heat, that means it's going to melt. Versus at 0 degrees Celsius, that same temperature, if I'm taking away heat, that means it's going to actually freeze. But all of those happen at the same temperature. So 0 degrees Celsius is important because that's a temperature where you can have either process. It just depends on if you're adding or taking away your heat. Same thing happens up here. So if this was still water, that would be 100 degrees Celsius. So here at 100 degrees Celsius, if I'm adding heat, That's when I know evaporation is going to occur, or boiling, right? Because that's the boiling point. Boiling is the name of the process that you'll also see. And then if I'm taking away heat though at 100 degrees Celsius, then instead I'm going to encourage my gases to go ahead and become a liquid and condense. But as a reminder, okay, processes only happen at your flat lines. Okay, all that happens at these is, at your slants, I guess, is heating. So here we can just say solid is heating. I'm heating my solid. Then here I get my liquid, so this is where the melting happens until it all becomes liquid. And then here my liquid is heating. Until I get all the way up to my boiling point, and eventually as I'm heating up my liquid until the point where all of my particles have enough heat, then it just becomes gas is heating. Because this is a heating curve. So we're adding heat always, but the processes only happen at the flat lines. Okay, now we have a cooling curve. What's different? What do you see that's different about the cooling curve?
It's going in an indirect direction.
Right, indirect, or like literally the opposite direction. Because with the cooling curve, instead of starting off at a low temperature, now we start off at a high temperature. Okay, we're starting off really high because we're trying to cool something down. So then my question to you, at a super high temperature, will we find water as a solid, liquid, or a gas at a super high temperature?
Gas.
Gas.
Right. So now with the heating curve, we're going to start off with gas only, because we're starting off at a high temperature versus with the heating curve, we started off down here. In this case, we're taking it down, taking the temperature down. So in that case, then I end up having my gas and my liquid here. And if I'm reading this backwards, what process is happening here then?
Condensation.
Right, it could be condensation, definitely, which is why I wrote that first, but depends. We can read these back and forth. So it could be vaporization. Vaporization is 2, depends on which way we're going. Okay, then after then, once it all fully condenses, I end up getting my liquid only. And then at this point, I cool that down until I have liquid and solid. And then that process here is going to be freezing or melting. Okay, and then all the way up until the point where I've taken away as much heat as possible or enough to slow everybody down and for that entire sample to become my solid or my solid only. So even still, we still have our processes happening at our flat lines. So even if it's a heating or cooling curve, okay, the processes still happen at the flat lines. It's just up to you to make note of the fact that they happen in different places. But as long as you remember, condensation and vaporization always happen at high temps. So on the cooling curve, our high temp is on the left side versus on the heating curve, we saw it on the right side. Versus your melting and freezing, that's going to always be the lower temp. Or in this case, if you look at it as a stair step, the melting and freezing is going to always be the lower step, because it happens at a lower temperature. Just giving you different ways to think about it, because you're going to see questions where you're labeling it, or they're just going to ask you things about the graph. So let's just go ahead and see an example of that so we're on the same page. So here, what is the boiling point of this substance? So when you answer a question like this, first you have to ask yourself, where does boiling happen? So we just talked about it. Boiling, it's a process, so I know it's going to be the flat line. So is it boiling happen at the lower or the higher step?
The higher step.
Right, it's going to happen. Thank you. It's going to happen at the higher step. right? But boiling point is a temperature. So they're not asking me for a letter, they're asking me for a temperature value. So if we trace this over, what temperature do we get?
140 Celsius.
Oh,
Yes,
no.
140 degrees Celsius. So that's what my boiling point is. Or if instead of boiling point, if that said, where does boiling occur? What would you say?
100 degrees Celsius.
So that's different. What and where? So if they're saying where this time, they're asking you where on the line, or they're asking for a segment.
Between D and E.
14 to 18 minutes.
Mm-hmm. So yes, you can say a couple of things. I like the fact that somebody used that. So if they said segment, then they're asking for the letters. Or if they said when, right? If you look at the bottom, they changed it. Now they're giving us time. So then we'd say, oh, it happens right here, like somewhere between 12 and 14, all the way up to 18. Okay, so it depends. See, those are like 3 different questions about the same section. It just depends on what they're actually asking for. So you have to be really careful with that. Okay, another question. During which section will you find both liquid and the gas? Which section? D and E, right? Because this is liquid only. This is gas only. So that means you can't have solid here. You always have it's in between. So this is going to be your liquid and your gas. So your answer to this one, yes, will be right here at DE. Okay, let's try another one. So now it's a little bit different. What is the freezing point of this substance? Now notice this is backwards now, so this is a cooling curve.
D and E.
You said D and E?
Yeah.
Yeah, that's where freezing happens. But remember, freezing point is a what?
A number.
It's a number, right? That specifically, that is a temperature value. So at D and E is where it happens, but what's the temperature that this happens at?
50 degrees Celsius.
Right? And that would be 50 degrees Celsius. Yeah. So then just get practice as far as reading these. All right. Quick question. When does the liquid first appear?
Between C and D.
Remember, it's going to first appear at a point. So this is going to be a letter. When do you first get liquid? I heard B, E, they all sound the same. B as in boy or E as in Edward?
D as in dog.
Okay, I heard D as in dog, so I'm hearing here. Anyone else?
E as in Edward.
E as in Edward. Okay. Anyone else?
C as in cat.
C as in cat. Okay, so let's go ahead and label this. So here we have our solid only. Then here we have liquid and solid. So liquid is here, yes. Here we have liquid only. And then what do we have here between B and C?
Condensation.
Condensation, but as far as states, what states do we have between B and C?
Liquid and gas.
Liquid and gas, and then this is only gas. So then my question to you is, what you guys missed? When do we first see liquid? When do we get our first drop of liquid?
Point B.
E.
Right here at B, right, exactly. So see how tricky that can be? Like we know liquid is here, which is why everybody focuses on the lower part of the graph. But remember, you first get a drop of liquid, and I heard it when condensation starts, because that's when you start going from your gas to your liquid. So your first drop happens here. Okay, so now I'm going to give you guys a minute to try this one on your own. Okay, so don't put in an answer, but I'm going to give you a minute. Let's see what you come up with. So first we have to break this part. How long will it take for the substance to cool from the time first liquid is observed? So we just talked about that part. We know we first get our liquid here at B. That's the first time we get it. Then they said to when it's fully a solid. So that's the second part. So when is it fully a solid?
Point E.
At point E, right? Because remember, this is where freezing happens. So at this point, you still have liquid and solid all the way up until you get to E, and then from E and on is when you have solid only. So now that we know my points, then how do I find the time? How long does it take? What's the last part?
You would have to
Subtract.
2 from 15 or
Right.
15 from 2.
Right, subtract 15 from 2 or 2 from 15, and that way you end up getting 13 minutes. And that's literally as hard as it gets, right? Just incorporating time and then just paying attention to when you first see something. That's the hardest part, just remembering when you first get in here, your first drop of water, or when you first get your first sign of a solid, right? That happens here. So just those are crucial points to remember. And otherwise, that's it for today. So what you have now, and I'm finishing early on purpose, so you have time to start this. You have homework. It's an online quiz, just based on reading heating and cooling curves. That's due tomorrow, Friday. But remember, you have 2 attempts. So we definitely have time now to make sure we get at least 1 attempt in. And that is it for today.